Hello and welcome to lecture 23 of our Essentials of Semiconductor Device Physics course. In this lecture, we're going to locate the Fermi level. In previous lectures, we found an expression for the concentration of free electrons and an expression for the concentration of holes. And both of these expressions depend on the Fermi level. So to be able to calculate the concentrations of electrons and holes, we need to find where is the Fermi level. And that's what we're going to do this time. This time we're going to find where is the Fermi level. So to do it, recall from lecture 19 that a semiconductor is a material that as the temperature approaches zero, then the conduction band is completely empty and the valence band is fully occupied. But as the temperature increases, electrons are excited from the valence band to the conduction band, leaving behind a hole. So each electron that was excited to the conduction band left behind a hole. That means that the number of electrons in the conduction band must be equal to the number of holes. In other words, the concentration of free electrons must be equal to the concentration of holes. But notice that this is only true because in the semiconductor, every free electron left behind a hole. If, for example, we had another material that at 0 kelvins there was already some electrons in the conduction band, then this equality would not apply. But since this is true in the semiconductor, we can use this equality to find the position of the Fermi level. So we can use these two expressions. So this is the expression for N, this is the expression for P. Now we manipulate them a little bit. We move this term to the other side, so it comes here. We move this exponential to the other side, so it picks up a positive sign. Here it's negative, here it's positive. Then the multiplication of exponentials we express in terms of the sum of the argument. Then we take the log on both sides to get rid of the exponential, and we end up with this expression for the Fermi level. Now recall that these two terms are identical except for the effective masses. So we can replace these two terms with their corresponding expressions and then express this ratio in terms of the effective masses. Since all terms will cancel, this term is reduced to this term here. And notice the power of 3 halves because of this power, and notice that we have Nd here in the numerator, and we have the effective mass of holes in the numerator because the effective mass here is in the denominator of a denominator, so it's actually in the numerator. Now we can get rid of this power by multiplying this term by 3 halves, and we get this expression for the Fermi level. Now we recall from the previous lecture that I mentioned that the effective mass of holes can be different from the effective mass of electrons because the interaction of electrons with the atomic structure depends on whether the electrons are in the conduction or in the valence band. But even though these two terms are usually different, they are sufficiently similar to allow us to dismiss the contribution of this term. So this number here is close to 1, so that the logarithm of a number close to 1 is something close to 0, because the log of 1 is 0. And that means that this is the main contribution to the Fermi level. So according to this expression, the Fermi level is in the middle of the band gap. So to find the concentrations of electrons and holes, now all we need to know is the band gap. If we know the band gap, then we know this distance, which is this term, and we know this distance, which is this term. Then we just need to plug in the numbers, and we also need to look up the effective masses of electrons and holes in the material. And in the textbook, there's a worked exercise using these equations that we derived to calculate the concentration of electrons in silicon. So we need to look up the band gap of silicon, the effective masses, and assume a room temperature. And that's the result as shown in the worked exercise. Now this discussion applies to what we call an intrinsic semiconductor, which is a term that means that the semiconductor is pure. But a major property of semiconductors is that we can control the concentration of electrons and holes, and hence the position of the Fermi level, in a very easy way using a process called doping. And that's the subject of the next lecture. So next time we're going to discuss how doping affects the bond structure of semiconductors, and hence the position of the Fermi level, the concentration of electrons, and the concentration of holes. So I see you next time.